Okay, now we are going to debrief question 4. So question 4 is a relatively interesting question, one of the school past year prelim question. So it's actually based on the computational studies. They give you this particular graph. So you might want to study it a little bit. Under three different conditions, one is under gaseous phase. It's under gaseous phase. You notice that when it's under gaseous phase, right, the final product has a much higher electronic energy or energies as compared to the starting material. Okay, and then when it's under cyclohexane, that's fine, slightly more endothermic, and then the transition states, it's maybe close to a late transition state, but not as late as the previous one. But when we use DMSO as a solvent, you realize that the final product is a lot more stabilized, and the transition state became an early transition state. Okay, so that is something that you can get out. I mean, the information you can abstract from immediately by looking at the graph. And we are really talking about the same reaction. That's between ammonia and chloromethane. The structure of the MSO is shown. I think that's fair because you're not supposed to memorize the structures of the solvent, but of course, if you know it, then that will be your advantage. Uh, and of course, you notice that you are given the nature of the mechanism. Okay, so you are given the mechanism being shown here. And what is more important is that you notice that your final product is actually charged. Okay, so there's a positive ionic center, cation, and an anionic center. Okay, so this might give you a little bit of clue as to why under DMSO, right, it is a lot more stabilized, or the reaction with DMSO releases heat, whereas in the gaseous phase, it doesn't release heat. Okay, um, so for part A, they ask you a relatively simple question. They said, explain what is meant by the pyramidization angle. So this is quite a mouthful. Pyramidalization angle. Wow. So if we if initially you're not sure what exactly this is, you might want to look at the starting point again or from the graph. You realize that they begin at about the same point, which is here, very close to minus 20 degrees Celsius, 20 degrees in terms of the angle, in terms of maybe this particular angle. And then in the course of this reaction, there's a 0 degrees here. So probably the zero, so it is probably reference to a certain plane, probably. Okay, and then towards the end, you realize that the angle is around the same as well, around 19 degree. Okay, so if we were to look at this particular reaction, okay, now how can the middle part be 0 degrees? Well, I mean, you can look at this as a plate. This is called a trigonal planar portion in the middle. So it's a CH3 trigonal planar portion. Okay, now if you look at this relative to maybe any of this atom, okay, H, you realize that the H lies on the same plate. Okay, so if you look if you look closely at it, maybe pyramidalization angle is probably the angle where the CH bond uh, is relative to the trigonal planar geometry in the transition state. Okay, in the middle portions. Okay, so if you try to explain that, then maybe you want to leave out the angle of reference. Okay, what are you referencing to? What plane are you talking about? Some of the answers we receive are quite vague. It's just like, oh, it's the HC angle. So what is the HC angle you're talking about? So it's not very clear from the answer. Okay, so if there's a need to draw, then you might want to illustrate it with a suitable diagram to show us what exactly, which angle are you talking about. Okay, and then it can be seen that there is an inversion in stereochemistry, which I think is rightfully pointed out by the change from negative to positive degrees for the angle. Okay, so if we take this as the reference, if we take the middle portion as the reference point, change the color, if we take the middle portion as a reference point, then before that, if it is negative angle from it, then of course after the course of the reaction is now positive. Okay, so the angle is now positive. So that kind of makes sense. Okay, so I think A is pretty interesting question. You introduce a new term, but in the course of the reaction, And of course, given the information, you should be able to come up with some possible explanations. Okay, and I think the rest of the parts, pretty much, I think when we mark it, pretty decently done. So describe the trend in enthalpy change under the different conditions. Briefly explain the shift in transition state along the coordinate under the different conditions as well. Well, if you were to look at this whole system, so let me just maybe erase it so that it's actually clearer. You will notice that in the course of the reaction, it goes from the gaseous phase to cyclohexane, the MSO, right? It becomes increasingly more exothermic. Okay, it becomes increasingly more exothermic as we go from the gaseous phase to cyclohexane to the MSO. Okay, and of course for cyclohexane and in the gaseous phase, the reaction is endo, but for the MSO is actually exothermic. Okay, so that really kind of like makes sense. For endothermic reaction, you are getting a late transition state. For an exothermic reaction, you are getting an early transition state. Okay, so that is something that you might want to think about when you answer part B, because we notice for some answers that the student try to explain B using the answer in C. Okay, which means you try to give the reasoning why it becomes increasingly more exothermic. However, that is not the point here, because if you look at part B, right, you are just required to briefly explain the shift in transition state under the different conditions. Yes, so the main focus here is that as we go from endo to exothermic reaction, the transition state shifts from late to early. I think that's all you need for part B. But for part C is a different thing, because for part C, you are supposed to explain why is it that under DMSO is an exothermic reaction, whereas it's gaseous is not exothermic. Okay, so in this case, I think we can understand from the fact that when we use DMSO, it's also written here, being a polar aprotic solvent, right? It's able to stabilize the charged product via ion dipole interactions. I think that is the main thing that you want to deliver when you are answering this question. Okay, so it's the ion dipole interaction that stabilizes the products. So therefore, in the course of this stabilization, it releases a lot of heat. Okay, so however, for cyclohexane, it is non-polar. So the kind of interaction is formed with the products. It's largely dispersion forces. So dispersion forces, well, I mean, not too bad. Some heat is released, but then probably not enough to make the reaction exothermic. Okay, then for D, D is the interesting part. They ask you to sketch the transition states, okay, of the reaction between ammonia and chloromethane in the gaseous phase and in DMSO. So if we are looking at ammonia and okay, sorry, if we are looking at a gaseous phase, so over here is a gaseous phase, we are actually looking at a late transition state. Okay, so take note of it, it's a late transition state. So when we are sketching for a late transition state, right, what we want to focus on is, oh, sorry, maybe I should put the H the other side. So this bond is almost formed already, it's carbon. Okay, and then we want to tilt it properly, and then this bond is almost gone. Okay, so this is the transition state that we are talking about. Okay, and in terms of the charge, because you are supposed to indicate the relative size of the charge as well, so this will, I would say, the delta minus should be larger than the one we're going to draw next for the MSO, and then this delta plus should be almost fully divided as well. Okay, whereas for DMSO, right, being an early transition state, let me just find a place to draw. Maybe I'll draw it here. Okay, so being an early transition state, the N C bond is not really fully formed, so it's far away. Okay, the CCl bond is not fully broken. Okay, and then of course, we are still getting this particular geometry that we are expecting. And then of course we want to show that it's a transition state, and then in terms of the charge, the partial charges, it will be developing, but very little. So I'm going to put a small delta minus here and then a small delta plus here. Okay, so that's what it means when we say we need to show clearly the relative bond length, positions, as well as the relative size of the charges that develops. And then for the final part, when we are using methanol instead of DMSO, the rate was found to decrease significantly. Okay, significantly. What do you know about methanol? Methanol is actually a polar protic solvent that is able to form significant hydrogen bonds, not only with the products, but with the nucleophile. In this case, the nucleophile is ammonia. So when it forms significant hydrogen bonds with the nucleophile, in this case the lone pairs of electrons on N, it decreases its nucleophilicity. Okay, or you can say that it stabilizes the nucleophile so that if you assume that the stabilization of the nucleophile is much greater than the stabilization of the transition state, then you are going to expect the activation barrier to be way higher. Okay, so if you're not exactly sure what I'm talking about, you can refer to the activity 4 that we did previously. Okay, so now because the nucleophile is a lot more stabilized, the activation barrier is a lot higher, so I would expect the rate to be significantly slower because rate of action is correlated to activation barrier. Okay, or you can explain it by focusing on the fact that now my nucleophile, the lone pairs of electrons, is surrounded by the methanol molecules, highly stabilized, not so available to actually perform the nucleophilic attack at the electron deficient carbon center of chloromethane. You can do that as well. Okay, so remember for novel question like this, very importantly, you need to relate to what you learned in both your H2 and H3 and then try to elicit important information off of there. Okay, so